You've probably done this 100 times. You open your terminal, type kubectl apply, and a few seconds later, your container is running on a machine somewhere. But have you ever wondered what actually happens in between? That single command kicks off a chain of events involving at least 5 different components, spread across multiple machines, all coordinating without a single central brain telling them what to do. Your YAML file gets parsed, validated, stored in a distributed database, picked up by a scheduler, assigned to a machine, and handed off to a container runtime, all in a matter of seconds. Today we're going to trace that entire journey, step by step. By the end of this video, you'll know exactly what happens behind the scenes every time you run kubectl apply. Let's start with why we need Kubernetes in the first place. Running a single container on a single server is easy. You pull an image, start a container, and you're done. But now imagine you're running a real production system. You have 10 different microservices, each needing multiple replicas for reliability. That's 50 containers spread across dozens of machines. Suddenly you're drowning in questions. Which server has enough CPU and memory? What happens when a server crashes at 3 a.m.? How do you roll out updates without downtime? How do containers on different machines find each other? Managing all of this by hand is a nightmare. You'd need to track every container, every machine, every failure, every restart. That's an impossible job for a human. This is exactly the problem Kubernetes solves. It's a container orchestrator. You tell it what you want, 3 replicas of this service, 2 of that one, and Kubernetes figures out the how. Let's look at how it's built. Every Kubernetes cluster is split into 2 halves, the control plane and the worker nodes. The control plane is the brain. It makes all the decisions, what should run, where it should run, and what to do when something goes wrong. It has 4 core components. First, the API server. This is the front door to the cluster. Every request goes through it. Second, Declarative. This is a distributed database that stores the entire state of the cluster. Third, the scheduler. It decides which worker node should run each container. And fourth, the controller manager. It watches the cluster and fixes anything that drifts from the desired state. On the other side, you have worker nodes. These are the machines that actually run your containers. Each worker node runs a kubelet, which is an agent that takes instructions from the control plane and manages containers on that machine. Let's dive into each component, starting with the API server. The API server is the single point of contact for everything in the cluster. Every kubectl command, every internal component, every piece of automation, they all talk to the API server. When you run kubectl apply, your request hits the API server first. It goes through a pipeline. First, authentication. Who are you? Then authorization. Are you allowed to do this? Then validation. Is this a well-formed resource spec? If everything checks out, the API server persists the resource to Declarative. That's it. The API server doesn't schedule pods. It doesn't start containers. It simply stores the desired state and notifies anyone who's watching. This is a crucial design choice. The API server is completely stateless. It can be restarted, scaled horizontally, or load balanced without losing anything. All the state lives in Declarative, which brings us to our next component. Declarative is a distributed key-value store, and it's the single source of truth for the entire cluster. Every pod, every service, every config map, every secret, it all lives in Declarative as key-value pairs. Under the hood, Declarative runs as a cluster of nodes, typically 3 or 5 for fault tolerance. They stay in sync using the Raft consensus algorithm, which we covered in a previous video. As long as a majority of nodes are healthy, Declarative keeps working. Here's what the data looks like. Each Kubernetes resource gets stored under a path like registry pods default my app. The value is the full resource spec in a serialized format. One critical rule, only the API server talks directly to Declarative. No other component reads or writes to it. This gives the API server full control over access, validation, and consistency. Declarative is the foundation, and everything else builds on top of it. When a new pod is created, it starts in a pending state with no node assigned. The scheduler's job is to find it a home. The scheduler watches the API server for pods that don't have a node assignment. When it finds one, it runs a 2-phase process. Phase 1 is filtering. The scheduler eliminates nodes that can't run the pod. Not enough CPU? Filtered out. Not enough memory? Filtered out. Wrong architecture or missing labels, also filtered. Phase 2 is scoring. The remaining candidate nodes get scored on criteria like how balanced the resource usage would be, whether the pod's data is already local, and affinity preferences. The highest scoring node wins. The scheduler then writes the decision back to the API server. This pod should run on node 3. It doesn't actually start anything. It just makes the assignment. The actual work of starting the container happens on the node itself, which is where the kubelet comes in. The kubelet is where the rubber meets the road. It's an agent that runs on every worker node, and its job is to make sure the containers that are supposed to be running are actually running. The kubelet watches the API server for pods assigned to its node. When it sees a new pod, it kicks off the container lifecycle. First, it tells the container runtime, usually containered, to pull the image if it's not already cached. Then it creates the container from that image. Then it starts the container. The pod status transitions from pending to container creating to running. But the kubelet's job doesn't end there. It continuously monitors the health of every container. If a container crashes, the kubelet restarts it. It also reports status updates back to the API server, so the rest of the cluster knows what's happening on this node. Now that we know all the pieces, let's trace the full journey from start to finish. Let's put it all together. You type kubectl apply with a deployment file. Here's exactly what happens. Step 1. Kubectl sends the deployment spec to the API server. Step 2. The API server validates the spec and stores it in Declarative. The deployment controller notices the new deployment and creates the corresponding pod objects. Step 3. The scheduler detects these pods have no node assignment. It evaluates the available nodes, filters, scores, and picks the best one for each pod. Step 4. The scheduler writes the node assignment back through the API server to Declarative. Step 5. The kubelet on the chosen node detects the new pod assigned to it. It pulls the container image, creates and starts the container. Step 6. The kubelet reports back. Pod status is running. The API server updates Declarative, and kubectl can now show you a healthy, running pod. From YAML on your laptop to a running container on a remote machine. That's the complete lifecycle. Kubernetes doesn't just deploy your containers and walk away. It continuously watches the cluster and fixes problems automatically. Here's how it works. Say you declared 3 replicas of your app. They're all running on 2 nodes. Now imagine one of those nodes crashes. Suddenly you only have 2 replicas instead of 3. The controller manager detects this discrepancy. Desired state, 3 replicas. Actual state, 2 replicas. It creates a new pod to close the gap. The scheduler picks a healthy node for the new pod. The kubelet on that node starts the container. Within seconds, you're back to 3 replicas without any human intervention. This is the core philosophy of Kubernetes, declarative reconciliation. You don't tell Kubernetes how to do things step by step. You declare what you want, and Kubernetes continuously works to make reality match your declaration. That reconciliation loop is always running, always watching, always healing. So here's the big picture. Kubernetes is a declarative reconciliation engine. You describe your desired state in YAML. The API server validates and stores it. The scheduler assigns pods to nodes. The kubelet starts containers. And the controller manager fixes drift, making sure reality always matches what you declared. Each component has one clear job, and they communicate through the API server. No component tells another what to do directly. They all watch the shared state and react independently. This loose coupling is what makes Kubernetes so resilient. The next time you run kubectl apply, you'll know exactly what's happening behind the scenes. Your YAML travels through the API server, gets stored in Declarative, gets picked up by the scheduler, handed to a kubelet, and becomes a running container. That's the journey from kubectl to running containers. Thanks for watching, and if this helped you understand Kubernetes better, make sure to subscribe for more deep dives into how things actually work.